Hypothesis testing follows a structured and systematic process. Rather than making decisions randomly, we follow a clear sequence of steps that guide us from the research question to a conclusion based on data. There are four main steps: stating the hypotheses, formulating an analysis plan, analyzing the data, and interpreting the results. The first step is to state the hypotheses. We begin by identifying the population parameter of interest and then writing both the null hypothesis and the alternative hypothesis. We also decide whether the alternative is one-sided or two-sided. A key idea in this step is that the hypotheses should clearly reflect the research question. They must also be written before we look at the data so that our conclusions are not influenced by bias. The second step is to formulate an analysis plan. In this step, we choose the significance level, often called alpha, which represents the probability of a type 1 error. We also select an appropriate test statistic. When creating the analysis plan, we need to consider the type of data we have and whether certain assumptions are satisfied, such as normality and independence. We also confirm whether the test is one-tailed or two-tailed. The third step is to analyze the data. Here we compute the test statistic using our sample data and determine the p-value. This step is often carried out using statistical software such as R, JMP, or Excel. Behind the scenes, these calculations often involve standardizing the statistic and comparing it to a probability distribution, such as the t-distribution, the normal distribution, or the chi-square distribution. The fourth step is to interpret the results. We compare the p-value to the significance level, alpha. If the p-value is less than alpha, we reject the null hypothesis. Otherwise, we fail to reject it. But interpretation does not stop there. We must translate our conclusion back into the real-world context, considering both statistical significance and practical importance, as well as the possibility of errors. Let's walk through an example involving patient wait times in a hospital. Administrators claim that the average wait time is 30 minutes, but a patient advocacy group believes it is longer. A sample of 40 patients is collected, and the average wait time is 35 minutes with a standard deviation of 12 minutes. We set up the hypotheses so that the null says the mean is 30, and the alternative says the mean is greater than 30. Using statistical software, we compute a test statistic of about 2.635 and a p-value of about 0.006. We compare this p-value to our significance level of 0.05. Because the p-value is less than 0.05, we reject the null hypothesis. This means we have sufficient evidence to conclude that the average wait time is greater than 30 minutes. From a practical perspective, this difference of 5 minutes may be meaningful. It could indicate issues such as overcrowding or inefficiencies that affect patient satisfaction. We can also construct a confidence interval for the mean wait time. In this case, the 95% confidence interval ranges from about 31.16 to 38.83 minutes. This interval lies entirely above 30, which reinforces our conclusion that the mean wait time is greater than 30 minutes. However, because the interval includes values below 35, we cannot conclude that the mean wait time is greater than 35 minutes. Putting everything together, we can summarize the hypothesis testing process as a four-step procedure. First, state the hypotheses and decide whether the test is one-sided or two-sided. Second, choose the significance level and test statistic. Third, compute the test statistic and p-value using data and software. Fourth, make a decision by comparing the p-value to the significance level and interpret the results in context. The key takeaway is that a hypothesis testing is a structured and transparent process. By following these steps, we ensure that our analysis is consistent, reproducible, and meaningful for decision making.